So last time we talked about the Standard Model just as an introduction, basically listing particles and talking a little bit about their properties. Today, I wanted to get into combining some of those particles, specifically combining the quarks and talking about hadrons, which are all particles made of quarks. They're given the name hadrons.
All right, well, all... Okay, I see. Right, yes. Okay, I was jumping ahead. So there's two types of hadrons, though, yeah. Right? There's the baryons and the mesons.
Right. Yep. So hadrons are quark combinations, any combination of quarks. And then you can split them up into two different groups, the mesons and the baryons, so all of this kind of like zoology of particles confused me a lot for a long time. And I want to blame it on one particular particle, which is the muon, which we talked about last time as the heavy electron, right?
Right. Yep.
Another name for the muon, at least when I went and like learned this stuff, maybe the first time, maybe the second time, one of the early times, someone in a book or a teacher or a video or something referred to the muon as the mu meson.
Right.
And the muon is the heavy electron, not made of quarks. But mesons are a type of hadron, quark particle. So right there, I was confused. Like from the beginning, I've been confused about these things and I haven't been able to separate them until like literally a month ago when you and I started talking about the idea of discussing the Standard Model. Because of that one confusing term, I just never put it together. And I still see references to the mu meson, but it's totally not a meson.
Right. Yeah. And so, but the reason that that's the case is it Yukawa?
Right.
So we had, in the 30s, I think it was, we had, baryons. I don't know if that's what we called them, but we had, the proton and the neutron. Mm-hmm. And then we had electrons and electron neutrinos. We knew, okay, we have these light particles. And lepton, I think, means light. And then baryons. And I'm not sure if bary has some root in heavy or something. Yukawa predicted a strong force particle that would weigh roughly 200 to 300 times, or 300 times, I think, the electron. And so that created this new intermediate class of particles. And they called those the mesons.
Right. Meso, like the middle.
Yeah. So anything that was heavier than electrons but lighter than protons and neutrons, because those are pretty close in mass, it was in this middle category. And so they went searching for that, for the particle that Yukawa predicted, and they thought they found it. And except when they looked at it in more detail, they found out that was the muon, but it was in that middle category of weight. So they said, oh, that's a meson. So it originally was the mu meson. And then over time, once we really started discovering quarks and stuff, we abandoned this categorization by mass or weight and went into this categorization by quarks, by the fundamental particles that we found out these things are actually made out of.
Right. And
so at some point, there was a transition where we said, okay, mesons are actually pairs of quarks and not heavier particles. So that's where that you must have either had an old book or a professor, who was working in the 60s or something when he learned this stuff. And so for him, it was the mu meson at the time,
right.
Or her, I guess I should say.
Well, it definitely wasn't I don't want to make it sound like it was definitely titled mu meson. It was usually given as sometimes called a mu meson or muon. They gave the two options, but they gave them an equal weighting. But right. I never caught on that it was it was just a leftover that didn't really make sense. I don't, for some reason, it tripped me up, confused me about the quark meson, which I think is actually what we call mesons now, as you said, made up of two quarks. Any particle with two quarks, that's a meson. But the mu meson, or what I think we should all just say muon and then leave mu meson in the past, and it's done.
Yeah. So if you see that term, immediately replace it with muon, and right. Know that mesons have to be made up of quarks.
Right. And muon is not a meson. Yeah, good. So we have the hadrons made up. Any group of quarks that we consider bound to make one particle, and those are all the hadrons, like the Large Hadron Collider is colliding quark particles. And you can have bound states of quarks that could be pairs of quarks, and specifically not just any two quarks, but one quark and one antiquark. And you can kind of see that from what we talked about last time, where we emphasized that quark, any observable quark particle has to be in a colorless singlet state. We talked about quarks having colors like red, green, and blue. And you can either combine red, green, and blue quarks, 3 quarks, and build up a 3-quark particle, which we call the baryons, or you can have a quark and an antiquark, which is also colorless. So 2 different ways to get a colorless particle. A quark and antiquark, those are mesons, or 3 quarks, 1 red, 1 green, 1 blue, and that makes a white particle or colorless particle, which is the baryons.
Right. And so, yeah, the one of the things I thought was interesting, is that there's the 2 ways to get a colorless thing. And by number, the 2 ways aren't the same. But by number, you could have a red, green, blue baryon. And that has, +1 red, +1 green, +1 blue. Mm-hmm. Or you can have a red, anti-red, or meson, and that's +1 red, -1 red. And so it's net 0 red, 0 green, 0 blue.
Right. But colorless.
Yeah. But those 2 are both stable, 1, 1, 1 or 0, 0, 0.
Right. Yep.
Or I guess -1, -1, -1, I think, as well.
Yeah.
Anti. Yes.
And I'm going to say this, but I know nothing about it, but you can get creative and come up with a way to combine a red, a green, and a blue, and then an anti-red and a red again, and have 5 quarks in a particle, which is called a pentaquark particle. And they pop up in the news every once in a while that someone claims to have found one or evidence for the possibility of one in a collision somewhere. But you can imagine higher numbers of quarks that can combine to make colorless combinations. But I don't want to get into those because I don't really know much about them, but I know that they're hypothesized to possibly exist in some situations.
Yeah, the only thing I know is that I think it's at Brookhaven. They're trying to look for states like that where they're colliding heavy ions. And then I think at Keck in Japan, they found a 4-quark state where it's essentially like 2 mesons. 2 regular quarks and 2 antiquarks, which also, again, are colorless.
Yeah, and it's kind of interesting counting, what is is the pentaquark, why isn't it just considered a baryon and a meson bound to each other, which it totally could be. And so it's kind of like, how do you count what the actual bound state is? Is it all 5 quarks interacting, or is it the 3 and the 2 interacting as 2 separate particles? So, yeah. But one way the 2 fundamentals is going to be some sort of meson and some sort of baryon, right? Right. That's most of what people talk about when they talk about the hadrons. Something to add is, if you remember from last time, quarks are what kind of spin?
They are 1/2 spin particles.
Spin 1/2 particles, right? So you can combine 2 of them, and they could have both spin up, both spin down, or 1 spin up and 1 spin down, and combine into a total spin of 0 or 1 or -1, right? So integer spins for the mesons. When you have 2 quarks, they can combine to make integer spins, which we said were a certain type of statistics. Those are bosons, which can combine in particular ways that the other type of particle cannot, in the statistical way of thinking about these particles. So mesons are integer spin particles, so they follow Bose-Einstein statistics. And then the baryons, the 3 quarks, you got 3 1/2 spin particles combining, and they always will combine into half integer spin bound states, bound particles. So the baryons are all what we call fermions, which have half integer spin, either 1/2 or 3/2 or, negative versions of those.
Which is really good and important, since protons are baryons, and if they had integer spin, we could just collapse them all in on each other.
Right. We would just, possibly collapse into ourselves if we were extremely cold, and just, live in the ground state, all happy, all of us together. But that's actually interesting. If you think about baryons, the quantum wave function, what it means to be a fermion in terms of symmetry. Do you know, Zach?
Are you talking about like parity? And if you, I think a fermion, when you swap two, you gain a negative sign. Exactly.
So if you swap two particles essentially in your fermion, which baryons are an example, you end up getting the negative version of that particle before the swap happened. So you can think of baryons of being made up of 4 different wave functions, meaning like you multiply 4 different parts of the baryon together to get the full wave function of the baryon. One is the space, just literally where is it in space? And you can kind of think of analogies to like the hydrogen atom, or like learning quantum mechanics with the Coulomb potential, where you have your n equals what, that determines how large your electron orbital is in an atom. So that's like the spatial wave function. So you have space, then you have spin. You have spin a half or spin 3 halves if they combine all together, something like that. You do have a flavor part of your wave function. So we have space, spin, and flavor. Do you remember what the flavors are from last time?
Yeah,
so remind our listeners.
Flavors are the same as or similar to, I guess not the same as, but it's essentially we have up, down, strange, charm, top and bottom, right? It's our type. It's essentially a type of that particle.
Mm-hmm. Yeah, what kind of quark is it? Right, exactly. And we got those 6 different flavors. And then the last part, so we have space, spin, flavor, and then the 4th one is the color, the thing we were talking about earlier, red, green, blue. That's the 4, components of a baryon's wave function. And I'm talking about baryons in particular for a reason, and we'll get into that in a little bit. But we can do some nice things and just kind of make arguments, since we know baryons are fermions and they have to be anti-symmetric, meaning swap 2 things, we get the negative. If you multiply a symmetric wave function by another symmetric wave function, the product is a symmetric wave function, right? And if you multiply an antisymmetric by an antisymmetric, you can imagine swapping 2 particles, and both of those parts of the wave function would get a minus sign and they would cancel out. So an antisymmetric and an antisymmetric product wave function would give you a symmetric wave function. But remember, we want the fermions, the baryons, to be antisymmetric. So we need either 1 antisymmetric of the 4 or 3 of the 4 being antisymmetric to end up with a net antisymmetric part of our wave function, right?
Right. Okay. Yeah.
You following?
Yes.
Okay. We can knock out 2 of those real quick. And the first one is just kind of a usual way that textbooks introduce the wave function of baryons, which can get pretty complicated. But the first way is to look at the spatial wave function and consider only the ground state, which is mostly what we're going to be talking about today. We might get into some excited states, but the ground state, just like in a hydrogen atom, remember the ground state of the electron orbital is just a sphere, like it's just a ball, right? So that's very symmetric. So the ground state for a bound baryon of 3 quarks, again, is just going to be symmetric. It has to be. There's not enough angular momentum possibilities for it to be not symmetric, right? So the spatial is symmetric. The other rule in physics, the color wave function, we said it has to be in a colorless state, but not just any colorless state. It has to be in a colorless singlet state. That's the only way to have an observed particle in physics, which I asked you offline outside of this podcast if there's any other situation where there's just kind of an ad hoc rule to physics where they say, yeah, mathematically, there's lots of different ways to combine the color charges of 3 quarks, but in physics, we only see this one version. Like you can think of the combination of red, green, and blue, and anti-red, anti-green, anti-blue. You can come up with lots and lots and lots of different versions of that. but physics requires that we have a singlet colorless state for our quarks, which is always anti-symmetric, the singlet states. If you think of like, they make a lot of analogies with like hyperfine splitting. Hey, the name of the podcast, hyperfine. I think that's the first time we've said it. But the hyperfine splitting in hydrogen, there's the singlet state originally, which is always an anti-symmetric combination of two electrons, or the electron and proton, or whatever you want to consider, or the quarks in this case. So there's just a rule just given to physics that says it has to be a colorless singlet state, which is always anti-symmetric.
So, sorry.
Yeah.
Remind me again. Okay, by singlet state, what do you mean there? Versus like what would be like a doublet state or a triplet state?
Essentially, the quickest way is if you imagine two quarks, or let's see, we have three quarks here. It's the spin 1/2 version. It's one up, one spin down. So a spin positive 1/2, spin negative 1/2, and then another one that could be positive or negative. But basically, it's not a spin 3/2 version, because there's like, imagine spin 3/2, your like spinner vector in space. You have multiple like orientations that you could take with that. Does that make sense?
Yes.
But there's only one spin value for a spin 1/2 combination of three quarks. So it's essentially the spin 1/2 state of the quarks.
Okay.
It's not a great explanation, but that's kind of, there's one unpaired quark.
Right.
Yeah. Okay, so we have spatial, which is symmetric. We have color, which is anti-symmetric. That leaves us with spin and flavor to make up the rest of our baryon wave function.
So can I say that at this point we know, okay, when we combine those two, we're going to get something that is anti-symmetric, right?
That's right. Yep.
Okay. So halfway through we are anti-symmetric.
Yep.
So that means
two more.
Yeah. So that means that somehow these other two must combine to be symmetric in some way.
That's right. Either they're both symmetric themselves, like spin and flavor are both symmetric, or they're both anti-symmetric.
Right.
Spin and flavor would be both anti-symmetric, but they can't be opposite symmetries.
Right. Yeah, because then we'd end up with a symmetric result.
Right. Again, this is for the ground state, but it's the most simple and it's worth talking about because it explains quite a bit. Okay, so after color, I want to get into the spin part of the wave function.
All right.
And the spin wave function can either be, like we basically already talked about this in the example of what a singlet state is. We have three quarks. They can be the spin 3/2 version where all the quark spins line up, or spin 1/2 version. The spin 3/2 version, imagine to build the 3/2 spin, each quark has to have its spin pointing in the same direction, right? They all have to add up together. So you can imagine swapping any two of those. That doesn't change anything. Right. So that's a symmetric version of the spin wave function if it's spin 3/2.
Okay.
If it's spin 1/2, you can have a combination where spin of quark 1 and spin of quark 2, maybe those are anti-symmetric, or you can have the spin of quark 2 and spin of quark 3 kind of combined to give you an anti-symmetric wave function. It's anti-symmetric in the swapping of two quarks to give a spin 1/2 baryon made up of three quarks.
Okay.
You follow that?
Yeah. So you're talking. So we have a baryon. It's made up of three quarks, and it has a spin wave function that goes along with it.
Right.
But then that spin wave, or maybe I should say, it has a wave function that's a multiplication of these four different types of these four states, right?
Right.
And when we're talking about the spin, that one is also then composed of a multiplication of the substates, essentially, of each individual quark. something along those lines. And so, yeah, I think what you're saying then is that combination can be symmetric or anti-symmetric, something along those lines. Okay.
And not only that, but it can be symmetric and anti-symmetric. Yeah, in the pair, like in a particular pair. Like swap 1 and 2, you get a minus sign. Or it's in a state where you swap 1 and 2, you don't get a minus sign, but you do swap 2 and 3, you get a minus sign. Like you can build up different combinations, linear combinations of quark spin states and have a particular spin wave function.
Okay.
And you might be wondering, what about the 1-3? It's not... you can build the 1-3 anti-symmetric state out of the 1-2 and the 2-3. Like you can get a linear combination of those to build up the 1-3 state. So it's actually not a linearly independent state for the quark spin function. Take my word on it.
Okay. All right. Yep.
Okay. So this is getting into like combinatorics of counting states, essentially. And I'm going to go into the flavor one after this, which is a little bit more complicated, which is why I wanted to start on the spin version. So we have 3 quarks, which each have 2 possibilities, spin up or spin down, right?
Right.
So in the combination space, that's not technically the word, but think of 2, but then that's for 1 quark. There's 2 options. But then you have multiply that by the 2 states for the other quark, and then multiply that by the 2 states for the third quark. You get a total of 8 possible spin states in the space of all the possibilities that the quarks can have. Like you can imagine like spin up, spin down, spin up, spin down, spin up, any combination of those things. You get 8.
Right. Yeah.
So that's just the rough counting way to figure out how many states possibilities there are. You can reorganize those and transform them into a group of 4, which is the symmetric spin 3 halves spin wave function. And the 4 states you can imagine is like way up there, spin 3 halves pointing as high as possible, spin 3 halves kind of pointing lower at an angle, right?
Okay.
Like imagine projections onto the z-axis is usually what we do.
Yep.
And then a negative versions of those 2 things. So we get 4 right there.
Right.
And then the other one, so would have a 4, and then we add to that the 2 for the spin 1/2 version, and then add the other 2 for the other spin 1/2 version. And remember, each one of those spin 1/2 versions are anti-symmetric in 1 and 2, or anti-symmetric in 2 and 3. So just number-wise, algebra-wise, we're taking 2 times 2 times 2 and saying that's equal to 4 plus 2 plus 2.
2 times 2 times 2 is equal to, okay, 4 plus 2 plus 2. Okay, all right.
So we still have 8 equals 8, but there's just different ways of organizing and grouping these things together. Different ways of looking at the same basic thing.
Yeah, so it's like, you can draw out like your little, it's almost like a truth table since it's binary.
Mm-hmm.
System for your 3, spin or quark 1, quark 2, quark 3. And if you just arbitrarily do it, you're going to, when you find all the combinations, you'll get 8 states. But then now you're going to say, okay, let's look at this a little more intelligently, and we can kind of come up with these overall ways of looking at it that gives us, a breakdown of these into smaller sets that we can say are similar because of the overall spin state.
Yep. So that 4 possible version group is a symmetric, the spin 3 halves spin state, and then the 2 spin 1/2 versions are both symmetric. We'll come back to that, but I wanted to go through that counting way of thinking about things because it's going to get interesting and become useful when we get into this last part of the wave function, the flavor wave function. And just like we kind of assumed that we're in the ground state for this baryon, let's work with what they were originally working with in this quark theory, which was only the up and the down quark, and then this third new quark, the strange quark. So what I want you to do, Zach, do you have a piece of paper and a pen? I didn't prep you for this.
Just got one right now.
Okay, awesome. What I want you to do is draw a line that goes out to start maybe, is it line paper or graph paper?
Yeah, it's the engineering paper, the green stuff.
Okay, cool. So give yourself 4 boxes worth of room above where I'm about to start. So imagine where you put your pen down as the origin. Have the origin be like at least 4 boxes, maybe 5 from the top of your paper.
Okay.
And make it maybe like the middle of your paper.
All right.
So you're about maybe 5 boxes down and middle of your paper. Draw a line from there up and to the left at some diagonal.
Okay. All right.
And then do another line up and to the right at a diagonal.
Okay. Right.
Hopefully at the same like diagonal angle in the other direction.
So now I have a little V.
You have a V. Perfect. And then draw a vertical line from the top of your paper down into that origin.
All right. So now it looks like I'm looking at the corner of a cube.
Yeah, it does. Perfect. Okay. So you basically, what I've had you draw is basically 3 axes. So just like if we had an X and Y grid, you would draw lines that are perpendicular to the X axis. So those would be vertical lines, right? If you marked off like 1, 2, 3 on your X axis, you would draw vertical lines that cross your X axis at a right angle, right? So this is going to get a little complicated and maybe use like dotted lines or like a thin line, but draw perpendicular lines evenly spaced on the left and right diagonal ones, going up from the origin. Just like make little tick marks maybe at like where your diagonal line crosses a grid spot.
Yeah, okay. So and then you want me to draw out those lines, right?
Just dash them like really lightly. They're not super important for what we're doing, but it'll help get things to line up. All
right. I'm there, I believe.
Okay, so you got perpendicular lines to your up and to the left diagonal, and then perpendicular lines to your up and to the right diagonal?
Yes.
Awesome. Okay, so this is part I'm going to try and describe. It's a little tricky. So from the origin, go up and to the left.
Okay.
To your first crossing.
All right.
And then go directly right to the other diagonal lines crossing. And where those 2 points, right in the middle of them, should be your vertical line. Make a tick mark there on that vertical line.
All right.
And then do the same thing on the next crossings of your diagonal lines. Wherever the line, the point right in between on that vertical line, make a little tick mark.
Okay. All right. Yeah. So I'm going to the diagonal. I'm going to call it the northwest direction. Mm-hmm, mm-hmm. And then I go to northeast direction. And
That's
then,
right.
And then I'll do it again at 3 northwest, 3 northeast.
Yep.
Okay.
Perfect. Okay. You should have, I don't think I told you how many tick marks to make, did I?
No, you did not.
Okay. At the bottom, you should have an origin, and then you should have up and to the left to be 1, 2, 3. Do you have at least 1, 2, 3?
Yes.
Okay. And then up and to the right, 1, 2, 3?
Yes.
And then, so on the vertical line, you should have also 1, 2, 3.
Yes, 4 if I include the origin.
And if you include the origin, they all have 4, right?
Yeah.
It's a little confusing because it's not technically the origin. So let me just have you put points down at each crossing. So it'll be really easy because there's the origin, and then up left again, up left again. There should be 3 points on that up left line.
Yep. Okay.
And then 3 points on the up right line.
Okay.
And then there should be a point. I want to point everywhere that the lines that are perpendicular from all 3 of your quote unquote axes meet.
Right. Okay. All right. So yeah. So I think what I can say is that's every intersection of the parallel lines is what you want, right? So I should,
yes.
If I have 3 things here, let me do it really quick. I should end up with essentially to me, it kind of looks like a 4x4 grid turned sideways.
Yeah. Yeah. It's exactly
16 points.
Right. Okay. So you should have a triangle, essentially. What I want you to do is stop when you get to the horizontal line that connects the highest
all right.
dashes.
Yep. Okay. So yeah. So then I cut that in half. I don't have
Yeah, don't keep going above there. Yeah.
Yeah. So I have a total of 4 plus 3. I think it's 10, if I remember correctly.
4, 3, 2, 1. Yeah, 10. That's right. I should have known that. I didn't even have to count because I'm going to tell you what this is in a second.
Those are my beer pong.
Yeah, exactly. Yeah.
Beer pong memories coming back from college.
Your triangle numbers. Right. Okay. And there should be one right in the middle also. Obviously, if you have 10, you got that one in the middle.
Yes. That one is there.
Now, let's label those axes with quark types. The up to the left is actually the down quark number. The downness, if you will. The up to the right is the upness. So this is your up quark counting.
Okay.
And then the vertical line is your strangeness.
All
S.
right.
And it gets a little weird because the 0 for strangeness is the 3 for upness. Like if you go the 3 for upness, that's the easiest one. Let's label the up axis. It's 0 at that origin spot I've been referring to.
Okay.
Up to the right is 1, and then another one is 2, and then 3.
All right.
And then go all the way horizontally left. Where that hits that strange axis, that's 0 strange.
Okay, so it's right in the middle of 2 points. Is that correct?
Yep.
Okay.
Yeah, there's no dot there, but that's a label of 0 strangeness on that vertical line. And then going down from there is -1 on the strange axis. And going down from there is -2 and then -3.
Okay, so the origin there is the thing that we've been calling the origin is -3.
-3 strangeness. That's right.
Okay, all right. And that must be -2, and that's -1. All right, gotcha.
And then up and to the left from that origin is downness, but it's actually negative. So it's -1, -2, and -3 going up and to the left.
Okay, so I've got my strange up-down axes.
Yeah, it's kind of weird. It's like 3 axes. It's like a 3-axis grid, but it's counting quarks essentially. Okay, so I'm gonna come back to that in a second, but we have our wave function for flavor, and that's again we're limiting ourselves to 3 types of flavors: up, down, and strange. So in our baryon, in the wave function, we have 3 quarks, which could be one of 3 different colors. So just like we counted the spin states wave function, we had 3 times 3 times 3. In the spin state, we had 2 times 2 times 2,
right,
because each quark could be up or down, had a choice of 2 things. This time we have 3 possibilities, up, down, or strange. So we have a 3 by 3 by 3 group, but we could combine those in different ways that are symmetric, completely symmetric, or we can have them be anti-symmetric in quarks 1 and 2, or anti-symmetric in quarks 2 and 3, or we can have it be in the singlet state. Completely anti-symmetric. There's no combination part of it. And if you organize those things, what you just drew, up, down, and strange grid, that is the symmetric version of that group. How many dots do you have there? I think you already said.
Well, yeah. So the intersection points, I have 10.
That's right. There's 10 places to intersect. And the reason we didn't keep going, like for example, we didn't extend the horizontal line of strangeness further upward because we only have 3 quarks. So at most, we have a strangeness of -3.
Right, which would be something like 3 strange quarks.
All 3 quarks are strange, exactly. And I mean, you could go into the antiparticles, which we're kind of ignoring, but it's a mere reflection of that drawing. It's the same combinations, it's just complete mirror reflections of it. So we're only working with non-antiparticles. And let me remind why strangeness is counted as negative and so is downness. It's based on what charge those quarks have. So down and strange quarks both have a charge of -1/3. So the NESS version of those quarks, like the strangeness and the downness, those are given negative values. So a strangeness of -3 means 3 strange quarks. And you notice it's nice because look at the -3 strangeness. It's 0 up quarks and 0 down quarks, which makes sense, right? The upness and downness is 0. It's all strangeness. That's your 3 strange quarks.
Right, yeah.
Okay, so what you've just drawn is the symmetric part of the 3 by 3 by 3. So what is 3 by 3 by 3? 3 times 3 times 3.
27.
27. So we should have a number plus another number plus another number, maybe plus another number, which ends up equaling 27. Just like we had 2 times 2 times 2, that's equal to 4 plus 2 plus 2.
Okay.
So what you just drew is the grid, and all those intersection points are the possible quark particles for flavor states that are the symmetric version. So we have 10 of the 27 possible states in that symmetric grid that you drew, the triangle of those points.
Right. Okay.
Cool.
Yep.
Those all have names. Each one of those points, those are all different types of particles.
Yeah. So each one of these basically exists.
Yep.
And maybe not this exact combo of things, right? But I believe along these lines is how Murray Gell-Mann predicted the omega minus particle.
Yeah, the omega minus is on your paper right now, and I actually just talked about it. That omega minus was not observed, but he saw that point down at what we called the origin with 3 strange quarks. They hadn't observed a particle that had a strangeness of -3 yet. So he observed that there should be a state there, and that's what he called the omega minus. And he, looking at patterns in the little drawing that you have on your paper, he was able to predict what its mass was, what its charge would be. He just said, this is a particle. I'm calling it omega minus. Keep looking. You're going to find it. And that's exactly what they did. So each little dot on your paper is a particle, and I can look up. This is called a baryon decuplet, as opposed to a baryon octet that we'll get to in a little bit. They're all this family, this thing that we're doing of drawing grids of different quarks is essentially this is called multiplets, the quark multiplets. And there's tons and tons and tons of them, and there's some for excited states. Remember, we're working in ground state only, and it's all about these combinations of how do you organize spins and flavors of particles to give you different bound states of 3 quarks or 2 quarks. We'll get into mesons in a little bit. So just going across your grid, you should have 4 on the top row, which are the lambdas. Those are all the lambdas. Lambda minus, lambda 0, lambda plus, and lambda plus plus. And I should say that usually, instead of drawing quark axes like I did, it's usually given in terms of strangeness and charge. And sometimes like isospin is worked in there as well. Those are the 3 grids that they label these as. And I kind of understood it, but I never really got it. And I know why they do it in textbooks. It's because that's how historically these were thought about, was something called strangeness that they observed in particles. But what that ended up being was just the strange quark amount. And then upness and downness leads to the total amount of charge, like proton and neutron, which we're going to see in a second. But across the top row, those are all your lambda particles. They have strangeness of 0. They're just a combination of up and down quarks that give different charges. And then the middle row that has 3 points, those are all your sigma particles.
Right.
Sigma star, I should say, because there's sigma mesons. There's other sigmas, but these are sigma stars. And the next one, I believe it's pronounced xi. It's the Greek letter with kind of like 3 bars. The top and bottom are a little longer. It's xi, yeah. Right?
I think, or is it? I don't know actually. I know most of the lowercase Greek letters. When you get the capital ones, I'm kind of I know the common ones.
So we got a xi star minus and a xi star 0. And again, the 0, then the plus and the minus are reference to charge amounts. For example, the delta plus plus has like an extra amount of charge compared to other ones. There's a delta plus, which has a charge of 1, and delta plus plus is a charge of 2. And then the final one down at the bottom there, 3 strange quarks, what we call the origin, that's that omega minus particle.
Right.
So this is the baryon decuplet, which is a way of combining 3 different quarks, all the combinations, into a symmetric combination of 10 states of the 27 possible ways to organize 3 quarks and 3 flavors.
Okay, so I may have a question.
Okay.
For you at this point. Maybe this isn't the best time to answer this question. Okay. So looking at this grid, if I go on my zero strangeness axis. I want to be at 0.
Mm-hmm.
And I go to 2 up and 1 down, or 2 down and 1 up.
Zero strangeness, 2 up, 1 down.
Or 2 down and 1 up. What are those particles?
Zero strangeness.
Sorry.
2 up and 1 down. I'm having a hard time. Oh, I see. Yeah, that's lambda plus.
Right.
Or I'm sorry. I keep saying lambda. It should be delta. I'm sorry.
Delta.
Completely. Yeah. Erase that word lambda. There's no lambda particle in what we just talked about.
Yeah. Delta.
All of that.
Across the top are deltas.
All of them are deltas. Yep.
Yeah. Okay. So we have a delta plus and a delta 0, I believe, are the
That's
two
right.
that I just said. Okay, but last week,
right?
We said, hey, I think you even quizzed me. What are 2 up particles or 2 up quarks and a down quark, or what are 2 down quarks and an up quark?
Mm-hmm.
Do you remember what we said last week?
Yep. So proton or neutron, right?
Right.
Yep, exactly. So these are combinations of protons and neutrons that are in, it's a different isospin state. We haven't talked about isospin, but you can kind of think of it as like a higher energy version of a proton and a neutron. They're identical. Really, the difference is the mass. That's kind of it.
Okay.
But it is something different with isospin.
Which is, isospin is just like the nuclear spin, right?
Yeah.
It's the spin of, versus, electrons have spin. Isospin is the same thing for the nuclear state, right?
That's right. Yeah. Just like, normal spin, there's nothing spinning, but it's a quantum mechanical number that distinguishes up and down quarks in different baryon states.
Gotcha. Okay. So it's a mass thing.
Yeah, it's essentially, that's it. I mean, you get people call this the particle zoo because, we have 6 quarks, but they can combine in, we think, only, so many countable ways, but then you get higher energy versions. Like if we're not working in the ground state, you can get the excited versions of these states, which are also deltas, but they're delta stars, delta stars. And, eventually they stop labeling them and they just say delta and then a number in parentheses, which is the mass, which just tells you it's a higher energy version of that particle.
Right. Okay. Yeah, I think I read somewhere that there was upwards of like 80 particles or something at one point back. Mm-hmm. So historically speaking, when we were doing this, is we saw the particles before we saw the quarks, and so we just had this huge list of what we thought were fundamental particles.
Yeah, these baryons, right? They just kept multiplying. Anytime you smashed them at higher energies, you kept getting more and more particles. And they're like, well, this is worthless. We just have this zoo of particles with no explanation. Yeah.
And then it wasn't until Murray Gell-Mann and there's someone else that at the same time had came out with the same idea as him, that he kind of arranged this decuplet or octets, and at some point was able just to kind of say, well, actually, I think all of this can come from 3 particles.
Right.
Zweig was this the other guy?
Yeah, Israeli guy, right? I believe.
Maybe, I don't know.
Maybe not.
If it is, I just said his name wrong, I think.
Let me just read straight from Wikipedia gods that say the delta baryons that are the analogs to protons and neutrons, like 2 up and a down or 2 down and an up. The delta ones are spin 3/2, like the baryon itself is a spin 3/2 particle and an isospin of 3/2. But the proton and the neutron are both spin 1/2 and isospin of 1/2. So it's these tables that we make, you draw like all the quark combinations and you say, okay, what's the total spin of the particles that I want, of the baryon or meson that I want to have? And then you fix that and then you say, okay, what states are possible with that combination? And we get 10 for this up-down strange combination baryon decuplet for spin 3/2. But now, exactly same table, exactly same number of quarks, but let's fix the spin to be a 1/2 spin state for the baryon in total. So, and to repeat, what you just drew was the spin 3/2 state of 3 quarks in a bound baryon state. Now we're going to talk about the spin 1/2 version. Same exact quarks, up, down, strange, same grid, nothing changes, but we're limiting our options to a spin 1/2 combination.
Okay.
So if we are in a spin 3/2 particle, do you remember if that was symmetric or anti-symmetric?
I believe it was symmetric, right?
It's symmetric. That's right. You change the states and nothing changes because the quarks are all spinning in the same direction, quote unquote. Right. So you change them, it doesn't make a difference. But if we are in a 1/2 spin 1/2 state of the 3 quark combination, now we get into some anti-symmetric versions. And we have a little bit of a problem. Where we have those deltas, the delta 0 and the delta plus as before, those are allowed. All the 3 where the sigma stars are, all those 3 in the middle there, those are allowed. And the word I don't know, I think it's xi.
Yes, I looked it up. It is.
Okay, xi minus and xi 0, those are allowed still. But we have problems in the corners of that triangle. So in the top right, the delta plus plus, that's an up, and an up quark.
Right.
Which you could see on our axes because it's on 3 on the up axis, 0 on strange, and it's 0 on D, right? Down quarks. So it's up, up, up. And then in the top left corner, that's a down, 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 a delta minus. And then the omega minus, which Murray Gell-Mann said should exist but hadn't been observed yet, and then eventually they did, which gave a lot of evidence towards this being correct. That omega minus, there's no spin 1/2 version. There's no way to combine up, 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 or down, 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 or strange, strange, strange in any way to get a spin 1/2 particle. And the problem with those is the Pauli exclusion principle.
Okay, so we're limited by our other quantum numbers to only have, like it boils down to, okay, we need to have different spins. And then once you have 2 in the same, you're kind of screwed. Is that
exactly,
it?
Exactly. There's no more places to put a quark state to end up with a spin 1/2 particle, but have the same flavor as the other 2 quarks.
Right, yeah, because then, flavor's all the same, spin is all the same, or spin would have to be, how does that work with, like the delta plus plus particle, when it's up, 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 they're all the same flavor, all the same spin. What were our other 2? Space and... Color.
Mm-hmm.
So they're all different colors. That's...
Right.
I guess that's the dividing one in this case, right?
Right.
For like the delta plus plus.
Right.
But for the equivalent in the spin 1/2 state, mm-hmm. couldn't we just have the same thing? Like can't they all just have different colors and then we're good?
Spin 1/2, we could be anti-symmetric. I think what you're getting to is correct, but my problem was that what I'm saying is like this is the flavor state. It's not that let me pick like delta plus, for example. It's not that it's the quark state is not up, up, down. It's not that. It's like an up, up, down minus up, down, up plus down, up, up all over root 3. It's like a linear combination of different things which have pluses and minus signs, and they are actually way messier than I'm making them out to be. But this is just a nice way to count how many of each quark there are. But sometimes you get an up, up, down. Sometimes you get a down, up, up. And they're in different linear combinations of those things.
Right.
So that's a non-answer to your question of can't you just do, anti-symmetric and symmetric, spin one half and have them be all up quarks. I don't think it's that simple. Like, it's not as simple as I'm making it out to be just quark counting.
Right. Okay.
So, sorry, that's not a real answer to your question, but it comes down to that basic fact that we're making linear combinations that are independent of each other, and the actual particles we're making base states that are independent of each other, and then the actual particles are linear combinations of those base states.
Right. Okay.
And there's actually a pretty good drawing in the Griffiths book, and I'm quickly trying to find it, where here we go. It's Griffiths' Introduction to Elementary Particles on page 176, and then continues to 177. If you have a PDF version, it's the PDF page 187. Textbook page number 176.
176. Okay. All right.
And then, the bottom half of the page shows the triangle that you drew. Maybe we have different versions of the book.
Yeah. Do you have the 2008 version?
Oh, I don't know. There's an equation 5.109 is on the same page.
Okay. No, I'm seeing like a graph is in the bound states thing, and it's on botonium.
Bottomonium?
Bottomonium, yeah. It's where I am currently on page 177.
Oh, no. I wonder if he moved chapters around or something.
What's the chapter on?
Chapter title is baryons. Or maybe that's the section. No, the chapter is called Bound States, and then the section is 5.9 baryons.
Okay. All right. In mine, it's 5.6 baryons.
Yeah. Okay.
I think I have found your triangle.
It's a big, huge triangle with really small writing of up, down, and down, up, and stuff like that.
Yes. Okay.
Yeah. So that doesn't really show it, but it highlights that these are linear combinations of quark states that make up these particles. Each one of those dots is two up and a down, but it's, different combinations of those things. And then, I don't know if it's in your book, but in mine, if you scroll a little bit further, you see the two anti-symmetric versions of the quark states.
Yeah, anti-symmetric in 1 and 2, and anti-symmetric in 2 and 3.
Yeah, so you lop off the corners of that triangle, and you end up with this, it's a hexagon with one point in the middle, right?
Yes.
Looking at your drawing on your paper.
Mine has 2 points in the middle.
Oh, in the textbook, yes.
Oh, yeah.
But the one that you drew is 1 point. Right.
Yep.
Yeah. So that's that hexagon, it gets you 6 states, and then you like you see in the textbook, there's 2 dots that end up being in the middle because there's 2 different ways to combine to get a spin 1/2 particle. There's 2 different ways to combine the 1 up, 1 down, 1 strange. Because that middle point should be 1, 1, 1 for all of them, right? 1 up, 1 down, 1 strange.
Right. Yes.
So, if you read about the baryon octet or the eightfold way from Murray Gell-Mann, what he's looking at, his eightfold way, is a graph of, he didn't know it, but it was the quark content, but what he was observing was strangeness and charge. And he organized them in this hexagon, which has 6 points. So there's 6 of the 8 particles. And then there's 1 point in the middle, but it's duplicated because there's 2 different ways to get combinations of the bound states of 1 up, 1 down, and 1 strange. And this really falls out of a group theory way of thinking about these things. Because this is another one of those mu meson that just threw me off. Everything was eightfold way and baryon octet, and I look at this, I'm like, I see 6 corners. What are they talking about? It's a hexagon. That's 6. And then they're like, well, it's 1 in the middle. I'm like, well, that's 7. Where's the 8? And then they're like, well, you double the middle one. I'm like, okay, I don't really get it. I still don't really get it. I'm not going to lie. I don't really get it. I can tell you that the difference between those 2 dots that are in the center is the isospin being 0 for one of them, and then the isospin being 1 for the other one. Isospin of 0 is the lambda 0. It's actually lambda. I got it right this time, not delta. Actually lambda 0 particle, which is up-down strange, one of each, and an isospin of 0, a spin 1/2 particle made up of up-down strange. And then if you have up-down strange, spin 1/2, but then have an isospin of 1, you end up with a sigma 0 particle. So that's what those two dots are right there.
But then this goes further, right? Because I think we've only talked about, so we can be anti-symmetric, like you said, you can be anti-symmetric in 1 and 2, anti-symmetric in 2 and 3, or anti-symmetric in 1 and 3 is a linear combination of the other two.
Right. That's right. Yep.
So
yeah. We got 10. I'm counting states again. We want to figure out where this 27 states of just blindly counting different combinations comes from. We got 10 for the symmetric decouplet. That's the spin 3/2 version, the table that you originally drew.
Right. Okay.
Then we said we're in a spin 1/2 state for our combination of 3 quarks. Lop off the corners of the triangle because I said so. because of Pauli exclusion principle, and because I can't really explain it further than that, and I don't understand it more than that. So that's essentially what it is. But you end up with the hexagon shape, but there are 7 points, but you double the middle one because of isospin states. That's your eightfold way. That's your baryon octet. And that's, like we said before, it could be anti-symmetric in that eightfold way, spin 1/2 baryon. It's anti-symmetric in particle in quark 1 and quark 2, swapping those two things around, or anti-symmetric in quarks 2 and 3.
Right, okay.
So there's 8 with the 1-2 anti-symmetric states, or 8 more with the 2-3 anti-symmetric states. So we have 10 from the decouplet, and then we have 8 and 8 for each of the 2 anti-symmetric octets.
So yeah, a total of 26.
So yeah, we're at 26.
So we're missing one combination. Yeah,
one combination, the singlet state, which is just a completely anti-symmetric in all 3 versions. And in that Griffiths book, it should be, if you scroll up a little bit, it's just a single dot. It's not a fun drawing, but it's there. And it's up, down, strange in a combination of, let me just read it, UDS minus USD plus DSU minus DUS plus SUD minus SDU all over root 6. And if you swap any of the U or D's in that equation, you should flip a minus sign somewhere. You should end up with the negative version of what you had originally.
Right.
Yeah. So that's a completely anti-symmetric state. That's the singlet. That's why it's called singlet, because it's just one. There's no other versions of that.
Gotcha. Right.
Yeah. So that's your 10 plus 8 plus 8 plus 1. And the Murray-Gell-Mann eightfold way baryon octet, those are those 8s. And then the decouplet is the 10. And then you got that singlet state.
Total of our 27.
Yep. 10 plus 8 plus 8, 16. And one more you got. Or 10 plus 8 plus 8, 26. Plus 1, 27.
Right. And so this was kind of like earlier we had our 2 times 2 times 2 is 8, or our 4 plus 2 plus 2 is 8.
Exactly.
So now we've broken it down into a 10 plus 8 plus 8 plus 1.
Right. Instead of a 3 times 3 times 3. Whew. So that's why Murray-Gell-Mann is, known as, I don't know, I'm going to say he's the godfather of quark physics, but he's the go-to guy, the origin of all this stuff. It's whenever you look up Murray-Gell-Mann, for some reason, there's always and somebody else. It's like Murray-Gell-Mann did it and somebody else did it at the exact same time. But then Murray-Gell-Mann's more famous. So the other guy usually gets forgotten. But somebody else organized things very similarly at the same exact time that he did.
Maybe it's just an American prejudice. Who knows?
Yeah. Yep. Is he American? I don't actually know.
Well, at least I think he was. I don't know if he was or at the time, but I think he taught at like ASU, maybe.
Interesting.
Oh my gosh! You go to his Wikipedia page. You look up. They have the picture of him, and it says "known for," and then
crazy amounts of things.
Huge list of things. Okay, sorry. I think it was Santa Fe or Institute or University of New Mexico when he kind of came up with. He was in there doing, I think he was probably Manhattan Project related work at the time. I think he was in that area.
Got it. So this is how it's kind of like a group theory way of thinking about things, going from just blindly counting how many ways can you combine up, down, strange, and then organizing them into a structured like table grid. You get these states that have some rhyme or reason to them, to the point where Murray Gell-Mann could predict a particle that hadn't been observed yet using his kind of like group theory methods.
Right. And also like he did the exact opposite of what we just did. We said, okay, let's combine up, down, and strange quarks. He combined particles
that were just no rhyme or reason. It was just like reaching in a bag and just being like, we've observed these, let's organize them.
Yeah. And then, he kind of made his periodic table, if you will, of particles. And then from there predicted 3 quarks. Right. Exactly. That's right. Yeah. The way I had you draw it, thinking about up, down, and strange quarks is completely not how most textbooks teach it. And it's completely not how Murray Gell-Mann did this. They usually talk about strangeness, charge, and maybe isospin. But to me, that was not nonsense, but it didn't stick in my brain at all as to why they were doing it that way. Because if you look at just charge and strangeness, you could make a rectangular, XY grid and have the same points, and it totally works. And that was the first thing I did when I went back to try and learn how this stuff works. I'm like, well, why can't I just make a rectangular grid? And you can, and it works just fine. But when you start realizing, oh, it's quarks, you actually want to get this into like a triangular grid. That's when it makes sense to have it in a triangle or a hexagon, triangular points on your potential particles. Right, yeah, because we need kind of to be able to draw 3 independent-ish axes versus he only had 2 things that he was working with, charge and strangeness.
Right. Yeah, so all of that goes into the baryon wave function, which again is fermionic, which is antisymmetric. So you need those spatial, color. Those are the easy ones. Space is always symmetric in the ground state. And then color is antisymmetric because it has to be in that singlet state. And then you get complications in the spin and the flavor, which gets into the group theory that we were talking about. And the flavors lead to the octets and decouplets that we were saying. And then, go ahead.
Okay, so I was going to say, we have these, we have the space and the color, which combined give us an antisymmetric state. So then, since we know that these are fermions, we know that the end state needs to be antisymmetric. So that means whatever combination of spin and flavor we have, that combination has to be symmetric.
Exactly.
So then, so that's kind of, I'm guessing that's somehow related to this limiting issue as well, as we have to have these 2 combos of states that lead us to a symmetric outcome.
Right. Yeah. And I said it's because of the Pauli exclusion principle, and I'm kind of just parroting things that I've read, which I believe they're true, but I looked into Pauli exclusion in like quark theory and quantum field theory a little bit more, because I came across one instance of somebody saying in non-relativistic quantum mechanics, like non-quantum field theory, the Pauli exclusion principle is just taken as a rule. Like it's just like I said, kind of like an ad hoc, like this is axiomatic almost. Like it's just like everything has to follow this because that's what we observe and that's it. And that would have been a perfect example to my question earlier of like, it's weird that there are 27 possible color states, but nature always selects that one singlet colorless state for the observed baryons. And you could have said like, or I was thinking, what other instances in physics do we have multiple mathematically correct options, but then for some reason nature just picks one? And that's kind of the Pauli exclusion principle in non-quantum field theory, quantum mechanics, because there's a ton of possible ways to organize electrons in an atom, But because of Pauli exclusion, they only select certain ones, right?
Right. Yeah. Like you're not going to have two electrons in the same shell, both being like point or spin up or something, right? We have to, even though that's like a feasible, combination you could make, you rule that out.
Right. Exactly. Yeah. So, but something else that someone continued to explain, that the Pauli exclusion principle is actually derived in quantum field theory from other axioms that they take in quantum field theory, like symmetry arguments in the group organizational theory of combinations of particles. Pauli exclusion actually falls out of it.
Yeah, I was reading that too. That was like one of the, that's one of the crowning jewels of QFT, or is that they were able to, instead of just saying, hey, there is this rule here, they proved it.
Right. Exactly. Cool. One other thing that I wanted to talk about is not baryons, but get into the mesons. And you don't have to draw much more. Just look at your octet, that little hexagon. Can you reproduce the hexagon? Just the points. You don't need to draw the lines, just to make it quick.
Sure. Yeah, I can draw a hexagon real quick.
Yeah, good. With the 1 point in the center.
Yeah. Okay. All right.
Okay. Just as before, the vertical axis, if there was one on your paper, you could imagine it. It's going to be measuring strangeness. And then up and to the right is going to be upness, and up and to the left is going to be downness. But the difference is the point in that center of the hexagon, which was the 1, 1, 1 quark content, like 1 up, 1 down, 1 strange before. That's now 0. That's actually an origin. It's 0 strangeness, 0 upness, and 0 downness.
Sorry. Okay. One more time. Which point is that?
The point in the center of the hexagon.
Okay. All right. Okay. Okay, so that's 0 for everything.
0 for everything. Yep. And It's not 0 quarks, it's mesons, remember. So now we're dealing with 2 quarks. And the way to get 0 strangeness, 0 upness, and 0 downness is to have, up, anti-up, for example. That would be 0, 0, 0. No strange, right. No up, no down.
Right, which seems then, maybe I don't want to jump the gun here, but that if you can do that for upness, you can do that for down and strange, right? You can have a strange anti-strange and a down anti-down.
Yeah, you would think, but it's again, it's a little more complicated because of these linear combinations. But let's put some numbers on these axes, and then we can start talking about what the particles are at these points.
Okay.
So on the vertical axis of strangeness, the origin is at 0, and then if you go up from there, that's a strangeness of +1.
Okay.
And remember, strangeness is negative, so any strangeness of +1 means you have an anti-strange quark. So anything up on your hexagon, there should be 2 points up from that origin. Not in line with it, but above it.
Yeah.
Those are both particles that have one anti-strange quark.
Okay.
And then you can imagine below, the 2 points on the bottom of your hexagon, those have a strangeness of -1. They have a strange quark in them.
Right.
And then if you go, if you go down and to the left, that's an upness of -1.
Okay. So that's an anti-up quark. Anti-up quark. Yeah.
Yep. And then if you go up and to the right, that's an upness of +1.
Right. So that's just a regular.
Mm-hmm. And then you can probably imagine the rest, but to give you the orientation of which number goes where, if you go up and to the left, that's a downness of -1.
Okay, so it's just a down.
Just a down quark. Yep. And then down and to the right is +1 downness.
Okay.
So again, this is not the way it was originally defined. It was originally strangeness and charge and isospin. But in my head, this explains these drawings so much more than anything I've seen elsewhere. So I wanted to highlight that really it's a nice way to organize the 3 quarks. Historically speaking, that's not how it was done, but it's just to draw these drawings, pick 3 quarks, fix your spin, and then figure out the combinations, and that's all you got. But this is actually easier because it doesn't really matter. Like there's no decouplet for an up-down strange combination of mesons. Like it is actually only this hexagon with one dot in the middle.
Okay.
So we don't have to make an argument about Pauli exclusion to get rid of the corners.
Right.
So yeah, how many different ways could you combine 3 different quarks up and down? You know, you can do the combinations again, but we basically have it here. And
right.
Yeah, go ahead.
Well, it's isn't it? It's 3 quarks.
Mm-hmm.
I'm trying to think if this includes into 3 quarks should combine. Is it 9 ways? Because each quark, like a strange, compare with 3 other quarks.
Right.
Each up quark compare with 3 other quarks. Each down quark compare with 3 other quarks. So a total of 9.
That's right. But again, this is why those names octet and decouplet, I hate them because they confuse the hell out of me. And it's a 9 combination thing, but it's a hexagon, which I think of 6, but I know there's a point in the middle, so that's 7. But then we saw in the other one, sometimes you double it because isospin, so that's 8. But then here in quarks, we're in 9. I don't know. Let me tell you like how it's usually explained as the meson octet. So we're going to ignore a 9th version for a second. Good?
Yes. But look, I was just going to throw out there that there's glancing at when I was reading through Griffiths yesterday, he did talk about octets where it's the same 6 corners plus 2 in the center somewhere. And then he also mentioned, and I'm trying to find it really quick, nonets.
Yes.
Which are 9. Was that so? I'm presuming maybe we'll talk about different things here, but
yeah, I mean it is a nonet, but usually people keep the 9th state separate.
Oh, okay.
Kind of like how we said there's the singlet state. We didn't draw a separate drawing for it, but you could have put it on the octet, right?
Okay.
Like you could have included it. It still had 0, or it had an up, a down, and a strange. It had one of each, but in a certain combination that it was anti-symmetric in all 3 flavors.
Yeah.
So similarly, we have the octet here. And that middle point in the middle of the hexagon has 2 particles associated with it, which again differ by isospin. And let me just give you some names of these particles. The top ones that have an anti-strange, those are K particles. So down anti-strange is K0. And then up anti-strange is K plus.
Okay, K0, K plus.
Yep. And then the left side, working along the middle of the hexagon, to the left is the pi minus, which is a down anti-up.
Okay.
And let's go all the way to the far right, which is a pi plus, which is an up anti-down.
Okay.
So
gotcha.
These are pi mesons. They're sometimes called pions. And sometimes the Ks, they get kaons. The name is kaon.
Yes, I didn't know if it was kaon, kaon.
Yeah.
Kaon.
It's a K meson or a kaon. Yeah. And then at the bottom, we got more Ks. So that at the top of the hexagon, we got K0 and K plus. And at the bottom, we have strange anti-up and strange anti-down. Strange anti-up is K minus. That's the bottom left of the hexagon. And then K0, but it's the top left is K0, but we would call this one it's a anti K0, so it gets K0 bar, has a bar over it.
Right.
And that's one way to look at this meson is do antiparticles. They're exactly across from each other in the hexagon.
Okay, so like a pi plus is the antiparticle is the pi minus.
Right. Yep.
Which really makes sense, I think, when you look at, the quark content of it. You have an pi minus is down anti-up and pi plus is up anti-down.
Exactly.
So all 4 of those are antiparticles of each other.
Mm-hmm. Yep. And so you have the K0, which is neutral, but it's a down anti-strange. But another way to get the neutral K particle is a strange anti-down. So they're both neutral, but they have different strangeness values, and they're antiparticles of each other. Okay, that center place, there's 2 dots there in this octet. We have a pi0, a neutral pion, and then we have an eta particle. Sometimes it's called eta 0, sometimes it's just eta.
Do you know what the quark content of these guys are?
So pi0 is up anti-up minus down anti-down. And then you got normalization of 1 over root 2 out in front of that. And then the eta is up anti-up plus down anti-down minus strange anti-strange.
Ooh, interesting.
Yeah. Oh, I'm sorry. It's minus 2 strange anti-strange.
Oh, interesting. Okay, so these are really, they are, this is more than just like, hey, there's these 2 quarks, stuck together. It's really like a quantum state of
exactly
quarks.
Yeah. So that's the meson octet that we just explained with the pi0 and the eta being in the middle there. It's up anti-up minus down anti-down. And then the eta is up anti-up plus down anti-down minus 2 strange anti-strange. That comes from essentially building ground states of quark anti-quark pairs. I keep saying ground states when what I mean is like basis states, like linear algebra version of states. So we're setting up basis states that we build linear combinations of.
Okay.
Does that kind of make sense?
Yeah. Yep.
Okay. So the basis states they're combinations of. Hold on one second. I'm reading something that I was trying to find. Yeah, one basis state. So the basis states, one of them is the up anti-up minus down anti-down.
Right.
That's the pi0, the neutral pion.
Mm-hmm.
And I'm ignoring the normalization factors just to talk about the quark content.
Right.
There's another state that we could build, which is up anti-up plus down anti-down. So the pion is it's got the minus sign. You could build a state out of the plus, but there's no particle that has the plus. It's up anti-up plus down anti-down with a combination of some strange state, strange anti-strange.
Right.
So there's 2 ways to combine it. You can get up anti-up plus down anti-down minus 2 strange anti-strange. That's one way.
Right.
Or you can have up anti-up plus down anti-down plus strange anti-strange.
A single strange anti-strange.
Yeah. And it's a little bit different than that, but can I say it in like the actual mathematical ways with normalization content? So it's up anti-up plus down anti-down minus root 2 strange anti-strange over square root of 3.
Okay.
And that root 2 is kind of to normalize the strange anti-strange relative to the up anti-up plus down anti-down. And it works out to be up anti-up plus down anti-down minus 2 strange anti-strange all over root 6. I know it's complicated to follow, but the main thing I want people to understand is that we're building basis states out of an up anti-up, down anti-down combination with a plus sign between them. And then that with the plus sign combines with strange anti-strange in a particular way to get linear combinations. One of them is the eta particle. That's the one that has the minus 2 strange anti-strange.
Right.
That's the one that fits in the meson octet along with the pion, which is up anti-up minus down anti-down. It's the only one that has a minus sign between the ups and the downs.
Right.
The eta particle has a minus sign right before the strange anti-strange combination. That's eta.
Right. Okay.
So that fits on the octet. Then there's the singlet, the octet plus this one other state, which is the eta prime. Eta prime is up anti-up plus down anti-down plus strange anti-strange, all over root 3. It's the simplest way that you would think to combine up, downs, and stranges meson states.
Okay.
But it comes from building basis states, up anti-up minus down anti-down, and then the other basis state, up anti-up plus down anti-down. That's 2 basis states, and then also combine strange anti-strange. That's your third basis state. How could you combine those 3 basis states to end up with a particle that has 0, up, down, and strangeness? Those are the 3 different ways: the pi 0, the eta, and the eta prime.
Gotcha.
And the pi 0 is purely that one basis state with 0 of the other 2 basis states.
Right.
And then the eta has that one basis state with the plus sign between them, and then the strangeness mixed in. And the eta prime has the basis state with the plus between the up and the down, and then plus the strange basis state.
Right. Okay.
And that's that up, anti-up, down, anti-down, strange, anti-strange business. That's the eta prime singlet, which usually isn't included in the meson octet, but it does complete the combination of 9 that you were saying, possible ways of combining 3 quarks into a 2 quark, 3 quark flavors into a 2 quark particle.
And yeah, so in Griffiths, he does have this listed, and he calls it a nonette.
Yeah.
Yeah,
it is a nonette, I did say octet and meson octet because it's often referred to as meson octet in the eightfold way, and that's again why this stuff, I just was so confused by it in lots of different ways, and this was one of them. Like people saying octets and then saying, well, there's 10, well, there's 9, well, there's 8. Sometimes, what?
Right.
So, yeah. Murray Gell-Mann knew what he was talking about. There's a reason he called it an octet, but it really is a nonette if you count this other state. And the reason it's not counted, sometimes people say, is because the mass is so much higher. It's about double the mass of the second most massive particle. The most massive particle in the octet is around 550 MeV. And then the mass of the eta prime is almost 1,000 MeV.
Oh, okay.
So sometimes people say, well, it doesn't belong because it's more massive.
That seems like just a choice.
Yeah, exactly. So that's the meson, quote unquote, octet, but it's the way to combine up and down quarks, and strange quarks, sorry. But I think just thinking about these drawings that you see sometimes, these kind of triangular grids, there is a method to them. And that's where it comes from. And then you can imagine things get much more complicated if you were to throw in a charm quark. You need 4 axes now, and you can look up multiplets with charm quarks, and it's like these 3D pyramid structures, and like 3D, I don't know what the shape is, but like kind of like a soccer ball, I guess.
Yeah. It's like, they look like what do you call them? Like the Greek solids almost.
Mm-hmm. Yeah, the Platonic solids and stuff there.
Yes, yeah, stuff like that. I mean,
and you can imagine it's like take your drawing of these triangles and hexagon grids, but then extend them out of the page and into the page into like a 3D version of that. We're looking at a slice where charmed equals 0 of this like multiplet, and then you throw in the top quark, the bottom quark. Nothing with the top quark, but yeah. You can imagine this gets real complicated really fast, and then make the spin, not the spin, but make it not in the ground state, make it in an excited state. Then you get even more possible combinations. It gets really complicated.
Which is why there's a whole zoo of these things.
Yeah, exactly, and that's exactly right. Just make all these particles the same, except make them in an excited state, not the ground state. You have completely new particles. And an interesting explanation of, why don't we do that with atoms? Like, why do we take a hydrogen atom? We don't call the N=3 state extra, some other name other than it's still hydrogen, right? Like it's not in the ground state, but it's still hydrogen. And an explanation was that the masses, when you're in an excited state in a bound quark system, the mass becomes so much different that it's actually makes more sense to consider it a completely new particle. Like the E equals mc squared that gets added by making it excited nuclearly. I guess it's not nuclear, it's not a nucleus, but in the baryon, the mass difference is enormous compared to the E equals mc squared of the excited hydrogen atom. The mass difference it's there. It's actually, you can calculate it, but it's negligible. You don't even consider it really when you're thinking about these things. So we call all hydrogen states, whether excited or not, hydrogen. But if you take a quark and excite it, now it has a totally different mass. That's a different particle.
Wow, interesting. Yeah. So there's just tons of so we drew out one nonet or octet for mesons,
right?
And Griffiths here, this was in 2008. I'm reading the updated version. He says that there's 15 established nonets,
right?
Is what he's calling these. And though he says, in some cases, not all the members have been discovered yet. So, I mean, yeah, okay. So we just said there's 9 here, but then, you add all these other particles and you're up to, 15 times 9.
Right.
And those are all, I mean, I think those are, okay. I can't say any more than that, but I mean, just a whole mass of particles.
Right. Yep. Yeah. And you look at, if you just Google list of baryons, not even look at mesons yet, but baryons only, it's a table in Wikipedia that, has protons, neutrons up at the top, and then you have lambdas, lambda plus charms, lambda bottom, zeros, psi plus, psi zero, psi plus plus charmed. It's just a mess. Like all these different symbols with subscripts and superscripts, primes, stars. So there is a rhyme and a reason to them. Like all sigmas are either up, 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 or down, down, down. Like there's 2 ups and 2 downs. I believe that's true. Or sorry, it's a combination of 2 quarks that could be an up or a down. I think that's the naming of sigmas. So any combination of 2 quarks that 2 could be up or 2 could be down, or 1 could be up, 1 down, that's sigma. And then psi is any combination with strange. Like there's reasons to these names, but it's not even worth memorizing what they are. It's just quark combinations and excited states.
Yeah. I think the other way to say maybe what you just said, Derek, is I think sigma is looking at the what do you call it, the octet that we made earlier, is or the was it was the
decuplet?
Decuplet.
Yeah.
Sigmas are all, they have one strange, I think.
Well, I think they have one that's not up or down. I think that's what it is.
Oh, okay.
Because if you scroll further, there's like the sigma star plus subscript B. That's an up, up B. Up, up, bottom quark.
Oh, okay. All right. Yeah, I was just looking at the 3 up, down, strange combos. Yeah. Okay, I see.
The bottom one in the table is the omega minus BBB. Like that's how they write like the symbol for it. And then there's like omega star plus CCB. I mean, it's not that weird because it's, telling you it's an omega star, it's a positive, and there's 2 charm in the bottom. Like, but it gets kind of ridiculous. Like, I guess it's shorthand for like the linear combination with the root 2s and root 3s floating around. And like,
right. Yeah. And, I kind of, at one point I want to talk about, not today, but in their standard model thing, is kind of like the experimental side of the physics that happen here. Cause there's a lot of cool, theory and experiment, working, together in this really nice way. And I think, I just kind of want to stress how amazing it is that we were able, or we, when I'm including myself in this, that Murray Gell-Mann was able to, take all these particles that, we've just been listing and say, no, okay, all of that comes from three particles. Okay. So, I mean, you've listed ones that come from like 6 particles. But, the 27 things, just to take that and say, oh no, it's all simpler than this.
Right.
It all comes from these 3. That's just like an amazing thing. Because if we didn't have that, we'd have this huge, like, we wouldn't be in an easier place than when we started.
Right. Yeah, exactly. There's reference or books, or I don't know, I've seen it multiple times, the particle zoo. Like, we just have so many deltas and pi's and xi's and lambdas, psi's and j's and k's. It gets messy real fast, and there's way too many particles. So we just, thankfully, there's a structure underneath all of this, which is the quarks, the standard model. But yeah, and they combine in a particular way that follows logic and follows, there is structure to it. It just seems like a completely chaotic mess when you first look at it.
Yeah, I mean, it's not simple, but like, yeah, people like, Gelman and Feynman and stuff were able to come up with these really nice, ways of explaining it.
Mm-hmm.
I mean, Feynman, I don't know if he worked on quarks, but, the Feynman diagrams, which I think we'll probably talk about at some point, are just a great way of visualizing,
right,
what's happening without having to do all of this complicated math.
Mm-hmm. Yeah. And then, even beyond just the omega plus CCC, triple charmed omega plus whatever, you get into baryon resonance particles, which are the same particles, but just higher mass, like I talked about earlier. So they have the symbol plus, and then in parentheses the mass of it just next to it. They don't even bother making more symbols. It's just, here's the mass.
And then so I think, just to talk about a couple of other things really quick, there's potentially, we're looking for, like we started out saying, other combinations of quarks, because we need, okay, well, I guess one thing that's worth saying slightly is that because we need this colorless state to have a particle that exists, mm-hmm, we've never seen an individual quark.
Right.
And as of, I think right now, we don't think we will ever see individual quarks. Because even if you take a meson and you were to pull the 2 particles apart, the quark and the anti-quark, what would happen at some point, there'd be so much energy from pulling these 2 things apart that they would spontaneously spawn 2 new quarks.
Right.
And you just end up with 2 mesons. Mm-hmm. So like we can't isolate quarks. So to say that they exist is, like when you haven't viewed one on its own is a it might seem like a stretch, but we have, my understanding from what I've read is we kind of just have all of this structure that comes from quarks, plus additional experimental evidence of things that we'd expect from doing like neutrino scattering off of protons and that sort of thing that lead us to say, okay, we think that quarks do exist. They're not just this like nice mathematical tool for us. That this is a real thing that's in nature.
Right.
Yeah, and they're looking for potentially they're looking for these other quark states, but then also, we have the 3 generations of quarks right now: the up, down, strange, charm, and top, bottom. And I, from what I was reading, there's no real reason, right, that there couldn't be necessarily a 4th generation.
Yeah, I don't. Not that I know of.
Yeah, I think one of the quick overviews I saw in Griffiths was just like, yeah, there, it's possible. Mm-hmm. We might not be limited to 3 generations of things, and that's another thing to keep, out there on the horizon of physics are there other quarks.
Yeah, I think if there were another generation, it would be following the trend where the mass increases with each one. And if it's, if it keeps going beyond the top quark, which is so unstable, it doesn't even really form any bound states. I don't know if it's more massive than the top quark, if it's going to do anything, They say it decays so quickly that the physics doesn't have a chance to actually do anything. So does that even count as a particle? But yeah, it's possible. And maybe the top quark, it's so much more massive than the bottom quark, the next highest mass one. It's so much more massive. I could imagine that the next generation is actually less massive than the top quark. I mean, that wouldn't follow the trend, but there's such a huge gap that there's room for there to be something else.
Right. Yeah. Or, maybe, I don't know why there would be, but like with, an analogy in chemistry and atoms, we've found kind of like these islands of stability.
Right.
And, who knows? But I think one of the things I read is that like, Griffith's saying is that like at some point we're getting up to these, to produce things that we think might exist that were like high beyond these masses. The energy in the colliders is just unfathomably stupid, that we just wouldn't do it.
Yeah. Yep. Well, cool. Well, this is good. I'm happy I got to talk this out.
Yeah, great. So far we've, we kind of gave the overview. We talked about, then this time we talked about combinations of quarks, which are called hadrons. And I don't know exactly what we're going to discuss next time, but we still have kind of leptons to cover a little bit, or bosons.
I really want to go into some, like, what's beyond the standard model.
Okay, I feel like
there's more to talk about before that.
Yeah. I feel like we should save that for for last.
Sure.
Because I still think we have a little bit of things I was thinking about. We're talking about were like a little bit of QFT in general, like
like Lagrangians and stuff. Yeah,
and getting into Feynman diagrams.
Sure.
And what was the thing? This could be fit in wherever, but talk about like accelerator physics maybe a little bit, because that's kind of the things that are making these. I think it'd be interesting to also just talk about kind of like the experiments that were done to some degree, but that could, some of that I think can be fit into like one podcast. I think it would be interesting to talk about leptons at some point too, and then bosons.
Cool. Sounds good to me.
All right. Well, if you like this, then please share it, I guess.
Yeah.
If you find this interesting.
Fix our mistakes. I'm sure there are multiple.
As always. We're reading and learning about this at the same time, so we're just kind of, at least I am, I'm presenting, whatever I say is kind of from the bits and pieces that I've been putting together. Yeah.
I've been, I think we pick topics because we don't know much about them when we want to learn more. So it's our excuse to go study it.
Yeah. Okay. All right. Well, I guess I'll talk to you next week.
Yep. See ya.